When designing deep learning and machine learning models, one of the most common questions that we often ask is how to choose the last layer's activation and the loss function when designing neural networks. Now, the answer is it depends on what problem we are solving. If we are solving a regression problem, then the last layer activation may be different and the loss may be different. If we are solving a binary classification problem, then it is different, and so on. Now, usually, if we have say, a neural network or even a convolutional neural network, then the intermediate activations usually don't play a big role in terms of the syntactical correctness of the model. Usually, ReLU or even LU as the intermediate layers activations work pretty well. So, all intermediate layers activations, intermediate layer activations equals LU or ReLU works pretty well. That's works well for almost all problems. But the most important one is the activation of the last neuron. So last neuron activation is the most important question. That is, what activation should we have in the last layer to solve the problem? So we'll come back to this, but before we discuss when to use what activation, let's look at the various kinds of machine learning problems, supervised learning problems, and then come back to this table to summarize what last layer activation and what MAE, what loss to use for various kinds of problems. Supervised learning may be overall divided into two types. One is regression problems and the other is classification problems. Now, in regression problems, the objective is to predict a continuous real value. And a good example is predicting housing price or even predicting image quality. Anything where our output is not discrete but a continuous number, say maybe between 0 and 100 or 0 or 1000 or even between 0 and 1 as a continuous value is a regression problem. Now, when we say the output can be 0 or 1, say for example, you have a data where the output labels are only 0 or only 1, then in that case, this is not a regression problem. This is a classification problem. But if your actual output labels are 0 0.1, 0 0.5, 0 0.08, in this way, continuous values between 0 and 1, then this becomes a regression problem. So overall, if we are predicting continuous values and the problem itself, the data itself has continuous values as output labels, then this is a regression problem. Now, classification problems may be further divided into three categories. The first one is binary classification. In these types of problems, the objective is to predict the probability of one class. And this automatically implies the probability for the other class. Here's how. Say we would like to predict the probability that an image contains a human face. That is, given a picture, we want to predict whether the picture contains a human face or not. Face present or not. So if we design a model with one neuron at the end that predicts the confidence of having a face in the picture, and if this confidence ranges from 0 to 1, then this is automatically implying our prediction for non-face as well. Here's how. We can say that if the neuron's output is, say, more than 0 0.5, then the picture contains a face. And if the output is less than 0 0.5, then we can say that there is no face in the picture. So if we only have two classes, which is the binary classification problem, then single neuron, one neuron is enough. One neuron is enough because that one neuron implies the probability of just one class, and knowing the probability for this class automatically implies the probability for the other class. We can simply do, if the predicted probability is p, we can do 1 minus p to obtain the probability for the opposite class. So for binary classification, we only need one neuron as the last layer, and we only need to consider the activation for that neuron. Now we may also have multi-class classification where the labels are single. One really good example is to predict whether an image has cat, dog, horse, or rat, etc. So the objective is to predict the probability of various classes. In this problem, in multi-class classification problem, each picture can be classified into only one class. One class. So maybe this picture is cat. We may have another picture that is of horse, and another picture that is of, say, dog, and so on. The next type of classification problem is multi-class classification, but these are multi-labels. So when we say multi-labels, what this means is we may have a picture where this picture may have on one side cat and the other side dog. So the class that it belongs to is dog and cat. So in this case, the objective is to predict the probability of various classes independently. So they may not depend on each other. And the model is supposed to separately predict the probability for each class. For example, predict whether an image has cat, dog, horse, etc., or all of them, or some of them, right? Or one or two combinations of them. So in this way, we have these four overall, two largely, regression and classification. But considering the three types of classification problems, we have four different ways in which we could have our supervised learning problem. Now let's go back to our table to see what activations to use when for various problems. So if the problem is a regression problem and we are predicting continuous values, for example, price, right, which could range anywhere from $0 to, let's say, any really large 100, 1000K or some really large dollar, then the last layer activation must be either linear, that is no activation, or ReLU activation, which means we are trying to predict numbers more than zero, because ReLU only gives you positive values, zero or positive. And in this case, for regression problems, the loss that we should use is MAE, mean absolute error, mean squared error, mean squared logarithmic error, log cost, etc. We'll talk about a little bit more about all of these losses in later slides, but for now, these are the kinds of losses that we can use for regression problems. Now, there may be regression problems in which the output values or the actual numbers may range from 0 to 1. So even if the numbers actually range from 0 to 1 with continuous values in between, if it is a regression problem, then we still use the last layer activation as linear or ReLU. One good example is quality prediction. Say your labels range from 0 to 1 and we need to predict the quality continuous value between 0 to 1, then that becomes a regression problem. Very frequently, we accidentally use sigmoid as the activation, thinking that this is the problem has labels between 0 and 1, but it is wrong. And it is a common mistake to use sigmoid when we are actually solving a regression problem. Once again, since it is a regression problem, we will use similar losses, MAE, MSE, etc. For binary classification, for example, a good example problem is whether a picture contains a cat or a dog, only two labels. So maybe cat is a 0 and dog is a 1 and so on. Then the last layer activation should be sigmoid and not linear. So once again, your program will run, your model will compile, and your training will run fine, even if you have linear activation when you're doing binary classification, but your accuracy will be very low, relatively much lower when you use sigmoid. So in case of binary classification, the only choice for last layer is sigmoid. And then for binary classification, the only choice for loss actually is binary cross entropy, the default loss function for binary classification. Similarly, when we have multi-class single label problem, that is when we are classifying cats, dogs, or horses, and each picture only has one label, then the last layer activation that we should use is softmax, and this is what gives you high priority for only one class and very low priority for other classes. And in this case, the loss that we want to use is categorical cross entropy. So for many problems, this works out very well. And if there is only one or two cases in which the picture may contain cats or dogs, it's actually a good idea to convert that problem into multi-class problem by removing those one or two pictures. Now, however, if you have a lot of images, a lot of data sets where each row or each data point or each image may belong to multiple classes such that we have multiple labels, then in that case, what we want to use is not softmax but sigmoid. And then once again, we actually use binary cross entropy because we want to independently predict the probability for each class.